So let me try to remind you what we did yesterday and rectify some things that I said in a bit of a sloppy way, perhaps. So yesterday we defined, sorry, Dave. Yesterday we defined algebraic knots. And as Gregor pointed out to me after the lecture, I was a bit sloppy, slightly, not too much. But I said, okay, an algebraic knot is the link of a singularity, so I take a polynomial in two variables. I look at its zero set, and I intersect its zero set with a small sphere. And at the boundary, I get a knot. I did say it a bit out loud without writing. I get a knot or a link in general. And the condition that ensures that I get a knot is that f is irreducible, but not as a polynomial, but as a convergent power series. So for instance, if I take x squared plus y cubed, this is irreducible as a two-variable polynomial, but it's not locally irreducible in the ring of convergent power series in x and y. And in fact, this gives you the hop link as a link of singularity, even though the polynomial is irreducible. So if you want an actual knot, you don't only need the polynomial to be reduced, as I was saying yesterday, no square factors, but you also need that it's locally irreducible in the ring of power series. And then you're ensured that you get a knot as opposed to a link. But anyway, modulo this, you get, for an arbitrary f, you get a link, each of which component is itself algebraic. So you can take as a definition any component of such a link, and this would work. And also yesterday I mentioned, at the very end I mentioned that if you remove the zero set of f from the for ball, you get a fibration over C star. I forgot to mention that actually the structure of VF itself near the origin is really just a cone. So there's no topology in VF itself, topologically and not smoothly. Somehow smoothly it's more of a trumpety point than a strict cone point, but topologically this is a cone. So there's no topology on VF itself. The topology, if you want, is just determined by what happens on the boundary. What's interesting is what happens somehow around it. Anyway, this is enough for what I wanted to rectify from yesterday or to add from yesterday. And then we define the concordance group, which is just knots modulo embedded annuli in S3 times the interval. So we define algebraic knots and concordance / cobordisms. And we had a conjecture due to Rudolph that I wanted to say something about. That algebraic knots are linearly independent in the concordance group that I denoted with C. And actually what I want to prove today is Litherland's theorem that torus knots, so positive torus knots, are linearly independent. So this is the goal of today, and actually this is mostly an excuse to answer the question how that I asked yesterday, like how do we even prove such a statement? So let me introduce the main tool that we're going to use. Luckily, Sashka did a great job. Well, I wasn't here, so I don't know, but I was told that she did a great job at defining the ciphered form. So recall thanks Sashka, that the ciphered form is associated to a knot and a ciphered surface of F. By the way, the existence of a ciphered surface was not proved by Seifert, as I was told, but by von Tragin and Frankel before Seifert. Anyway, so this is just a 2G by 2G matrix where G is the genus of F, and the basis of H1 of F, which measures the linking numbers between elements of the basis and their push-offs in the positive direction with respect to the ciphered surface. So we get a 2G by 2 integer valued or integer matrix that I sincerely hope that Sashka called V, because otherwise, that would be wrong. You did call it V, right? Thank you, Sashka. And technically this is associated, again, not to just K, but to F and the choice of the basis B. So what do we do with such a matrix? I don't know, we play around. So definition, the Tristram-Levin, I don't know exactly what the correct order should be. Signature. This is perhaps not the first thing that you would do, but is the signature of the matrix 1 minus omega V plus 1 minus omega bar V transpose. Sorry, in Italy we tend to put the transposition to the left and not capitalized. I will try to stick to that. So this is a matrix. This whole thing is a Hermitian matrix. So it's diagonalizable and its eigenvalues are real numbers. So it makes sense to count how many of them are positive and how many of them are negative. And it makes sense to take the difference of those two numbers. And that's what I would call the signature. That's what I call the signature of this matrix.
So omega is a complex number.
So omega is actually a unit number, a complex number of unit length. So what is this? This is actually a function of k at omega is just the signature of this matrix. Really not the first thing that you would do, but. And what is this? This is a function, sigma k, well, that technically depends on f and on b, that goes from S1 to the integers. And let me also recall maybe something that you're perhaps more familiar with, which is the Alexander polynomial. Delta k, again, depending on f and on b for the moment, of k is the determinant of v minus tvt, which is just a polynomial of degree at most 2g. And so far, everything depends on the choices that are made. No. Yes.
You're allowing the like 0 and S1.
I'm allowing.
I've just seen the Levin signature with like the missing the top part. I think the complex number corresponds to like 1.
Yes, I can do it for 1, then the matrix becomes the 0 matrix and the signature is 0. Yeah. Not particularly interesting, but yeah.
Do you recover the classical signature if it's -1?
Yes.
Or maybe double the classical signature?
No, it's double the matrix, but the signature is the same. So yeah, what Jeff was asking is whether you recover the so-called classical signature, or Murasugi-Trotter, I suppose, signature of the knot, which is maybe something you're more familiar with. And indeed, if you plug omega equal to 1, you get something classical, -1, thank you. -1, you get the classical signature. Also, you have some symmetries. If you exchange omega and omega bar, it's actually the same function. So what's interesting is what happens on half of the circle. Great. Would be very, very, very sad if everything depended on the choices that we made, and it turns out that they don't. So we will actually prove that this is an invariant, and we will prove it the Rolfson way, which I really liked. I wasn't too familiar with this proof, but so let's do it in steps. Somehow this is the other way around than what people do ordinarily, but I first want to prove proposition that the signature of K is a lower bound in absolute value to the slice genus of K. This might depend on choices, but whatever the choice is, this gives me a bound on the slice genus. So, how do we prove it? I mean, we have two sides of the equation, and we want them to talk to each other. So how do we do that? We have our S3 here. We have our knot. I know, all my knots look like that, but. And we have a ciphered surface that I'll try to draw in color. Here of some genus G. And we want to make twice the slice genus appear. So what we do is actually we complete the picture to B4, and we choose a ciphered surface of minimal genus. So this is F. This is the F that we used to compute the ciphered matrix and the signature. And this is the F star that minimizes the slice genus for F. And now the key point is that if I take the union of F and minus F star, this is a closed oriented surface in B4. So it's now homologous. So it bounds, in principle, a 3-chain. But since we are in codimension 2, codimension 1, we can always smooth out the chains or choose chains that actually represent triangulated manifolds or smooth manifolds, depending on which category you want to live in. It's not that important in this dimension and codimension. But there exists M three manifold embedded in B4, whose boundary is F union minus F star. And now there's a key fact from three-dimensional topology that I will leave as an exercise and that maybe Livia will explain, or maybe you will figure out on your own. Whenever you have a compact oriented three-manifold whose boundary is a genus G surface, okay, unfortunately this is a G, maybe let me call this H, then the rank of the inclusion of the boundary into the manifold at the level of H1 is half of the dimension of the space. This is a genus H surface, so this is 2H dimensional, and the inclusion kills half of it. This is what's called the half lives, half dies principle. No. Okay. So half lives, half dies implies that the rank of the inclusion is equal to G plus G star, because the boundary of M is of genus G plus G star. And now a bit of linear algebra magic tells you that, so let's call, I would really like to call K the kernel, but this would be a bit too confusing. So maybe let's call N the kernel. No, let me call it lambda, the kernel of this inclusion. I'm sweeping some details under the rug, but bear with me for a second. This is G plus G star dimensional, and H1 of F inside H1 of the boundary of M is 2G dimensional. Now in your head, keep in mind that G star morally is smaller than G. So this space is more than half dimensional, and this is half dimensional. So they intersect along something kind of big. So the intersection between lambda and H1 of F is at least G minus G star dimensional. And what is this gadget? What is this space? This space is the space of curves in F. So these are curves in F that bound in M. They bound something in M. So suppose that I have two such curves. Can I draw two such curves? Maybe. Suppose that I have one curve here that lives in that space. It bounds something in M. And suppose that I have another one that also bounds something in M. When I look at the linking numbers between them and their push-offs, when I push things off in S3, I'm pushing F away from itself. And I can follow this movement inside B4 by pushing M away from itself. So this is a bit annoying to see, but what's going on if I compress dimension even further is that I have S3 here, B4 is here, M is here, and I have my curves that are both here, annoyingly, but they're both here. and they both bound something in M. When I take the Seifert push-off, I'm pushing the curves away from the surface, and I can follow this movement by pushing M away from itself. So when I do this, the surfaces that they bound become disjoint. So if I take two curves, let me call them alpha and beta, the linking number between alpha and the positive push-off of beta, this can be interpreted as, let's say that alpha bounds A and beta bounds B. This can be interpreted as the intersection between A and B. This is the four-dimensional interpretation of the linking number. If you haven't seen this, you can think about it. It's a cute exercise. And once you have this linking number, well, since these two are disjoint, because I can just push them off one from the other, this is 0. And this is for any two curves that are in here. So what should I do now? What I should do is I should take a basis for f, for h1 of f, that contains a basis for this subspace. Then I complete it to a basis, and I compute the Seifert matrix with respect to that basis. And I better make sure that doing this does not affect the choice of the signature, but this is somewhat obvious because the way the matrix V changes when I do a change of basis is by orthogonal matrix, an orthogonal matrix. And the same orthogonal matrix gives me the change of basis for the matrix that I use to compute the signature. And the signature is invariant with respect to orthogonal changes. So the change of basis does not affect the choice. So actually what I should have done is say it first, but the choice of the basis does not matter. So now I choose my preferred basis, and in this basis, the matrix V has a big block of size G minus G star that has all zeros. And then I have absolutely no control on what happens on the rest. But so this is V. But then also the matrix that I use up there, this is a square block which is on the diagonal, so it appears also in the transpose, and when I take a linear combination, it stays in the linear combination. So actually this same picture also works for 1 minus omega, 1 minus omega bar, B transpose. And now linear algebra tells you that whenever you have a block of these, a block of zeros like this, if the matrix is non-degenerate, then you have to have at least G minus G star positive eigenvalues and G minus G star negative eigenvalues. Why didn't you correct me, Jeff? I said something silly. No. So this is if the Alexander polynomial of k at omega is not 0. So at some point this condition should enter, and there's a condition that I have here in order to be able to apply this theorem, which is that the matrix be non-degenerate. And it turns out that so this matrix is non-degenerate if and only if the Alexander polynomial is non-vanishing. And this is a very, very, very silly trick that this matrix, you can actually pick out a 1 minus omega, and this is V, maybe omega bar, and this is omega plus V transpose, no, maybe I prefer this, bar, and a minus. So this is exactly the matrix whose determinant is the Alexander polynomial of K evaluated at omega bar. If you plug in T equal omega bar in the definition of the Alexander polynomial, you get exactly this matrix here. So this matrix is non-degenerate if and only if its determinant is non-zero. Say it again. There should be a bar where? Oh, yes, except that the Alexander polynomial is symmetric. It's self-conjugate. It's an integer valued polynomial, so yeah, so it's 0 at omega if and only if it's non-zero, if it's 0 at omega bar. But yes, you're absolutely right. So it's non-degenerate, and then I have at least G minus G star negative eigenvalues and at least G minus G star positive eigenvalues. And then there are only 2 G star eigenvalues that are left. And at worst, they're all positive or all negative. And in that case, the signature is just 2 G star. Otherwise, it's something less. So at most, no, exactly, 2 G star eigenvalues remaining. These two cancel out somehow. The positive and the negative ones, they cancel out when I compute the signature, and whatever is left is the 2 G star. So I get the required inequality. Small detail, well, not so small detail, but the fact that the rank of this of this map is G plus G star does not, strictly speaking, mean that I can find a basis of this subspace that extends to a basis of the whole space over the integers. I can do it over the rationals, not necessarily over the integers. Let's not worry about that. This can be fixed, but I want to be honest and say that there. So this statement is true over the rationals, but it does not mean that it's true over the integers. There are examples in which this fails over the integers. So somehow this subspace need not be primitive. The kernel needs not be primitive. But yeah, technical detail that I want to at least mention. Right. So as a corollary of this fact, if K is slice, then the signature of K is 0 almost everywhere. For all F. So now let's do something simple, a simpler proposition. Sigma of, yes, but there are finitely many. So almost everywhere it means actually everywhere except for finitely, possibly finitely many points. If I have two knots, K and K prime, and I pick two Seifert surfaces, F and F prime for the two, and I look at the signature by using their boundary connected sum of the two Seifert surfaces. This is the sum of the two signatures as functions everywhere. The proof here it's really, 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 really simple. Because what I do, I can pick a basis B and a basis B prime that are separate. So what's the picture? The picture is that I have my two knots that are split here. I have two Seifert surfaces that are somehow boundary connected summed. So here I have my K, here I have my K prime, here I have my F prime, here I have my F. And I just pick a basis that's obviously picked for me. I pick one for F prime, and the two sides do not talk to each other. Elements on the left are far away from elements on the right. They do not intersect, they do not link, they're completely disjoint. So the Seifert matrix associated to this boundary connected sum is just the block diagonal sum of the two Seifert matrices. It's a direct sum, in a sense. And if I compute the signature of any direct sum, this is the sum of the two signatures. I can diagonalize things independently, and then I just count the eigenvalues of one, the eigenvalues of the other, and the difference is just the sum of the differences. So what do we have? We have an additive invariant if we pick the right surfaces. That gives me a slice bound. And actually, let me add another thing, which is even easier, perhaps. If I take the mirror of K with respect to the mirror Seifert surface, then the signature just changes sign. The proof is more or less, well, it's similar to what we've done here. If you reflect everything, you just change signs of the linking numbers. So if two things, if one push off, okay, maybe you transpose as well. But if you have two things that link one and you push them off they link one when you push them off, if you reverse orientations, then they link minus ones. So the matrix, the Seifert matrix for F bar is just minus the Seifert matrix for F. Perhaps transpose, but up to that, we're fine. And then you just reverse signs of all eigenvalues. You can use the same matrices to diagonalize, but you change signs to eigenvalues, and so the signature flips sign. And a fun corollary of this is that the signature is actually an invariant. Why? Well, K, I said K bar. This is a notation that I had not introduced. I want to say the mirror of K and the mirror of F. But K connected sum, the mirror of K is slice. And so its signature is 0 almost everywhere. But this signature is the signature of K plus the signature of the mirror of K with respect to two possibly different Seifert surfaces. And this is just the signature of K minus the signature of K with respect to another Seifert surface. And this is 0 almost everywhere. So at least this is independent of F almost everywhere. It's actually true that it's independent all over the place, but this proof gives me at least that. I don't know, I really like this proof. The usual proof is a bit more cumbersome to me and requires a bit more technology somehow, but I like this proof because at the same time it gives you, it uses the lower bound on the slice genus to say something about independence of choices, which is fun because it's a priori something that is entirely three-dimensional, but you prove its invariance by going to 4D, which, I don't know, it's always cute. Yes?
Sorry, should it be the inverted mirror?
Yes. Thank you. But you're right. I should also say that the signature does not see the orientation of the knot. So if you reverse the orientation, you get the same signature. This is...
Just orthogonally inverting the orientation of the surface?
Yes. Yes. So I think in that case, you transpose the matrix, the Seifert matrix. Correct, Sashka? Ah, great. I mean, I give him away my own exercises, so. Good, thank you. That was a good point. More questions? Right. Now, computing things is hard. I mean, Gromov used to say that everything difficult in mathematics is linear algebra. Okay, it's Gromov, so should take it with a grain of salt. But there is some truth to that. Actually, doing concrete computations is tricky. You can do it for small knots. You will do it for less small knots, hopefully. But yeah, this is hard. And it's somehow manageable example by example, but doing it along families gets tricky. So it's a bit surprising when you can do computations. This computes signatures. So this is a theorem due to Briscorn and Litherland. So Briscorn computed something slightly different, and Litherland realized, oh, actually I can use this to compute what I need to compute. But the signature of TPQ can be computed from this picture. So, how? I need to compute the signature at a certain value omega. So let's fix omega equal e to the 2 pi I x. And I am looking at TPQ, and I want this to be the p direction, this to be the q direction, and I want to plot, actually maybe not a very smart choice. This is the q direction, this is the p direction, and I want to plot all integer points between 1 and p minus 1, and between 1 and q minus 1. So this is a p, so this is 1, this is a p times q box. And I fix some x in 0, 1. And I pick the line x over p plus y over q equal x, and the line x over p plus y over q equal x plus 1. These yes. Yes, that's very unfortunate. Yes, alpha. Except that my alphas look a lot like my x's, but oh, God. Thank you. So I pick an x and I look at lines that are parallel to the diagonal here. So this is x over p plus y over q equal 1. So I look at one line that is somewhere here and one line that is somewhere here. The picture is a bit random. So let me call this L alpha, and this is L alpha plus 1. So this is my L alpha, and this is my L alpha plus 1. And now I'm counting points that are, let me think for a second. I want to count points that are in between the two lines and points that are outside the two lines. So the signature of TPQ at omega, that omega, is the number of red points minus the number of blue points. Sorry, I'm going to raise the board a bit. So in this picture, I chose hopefully p equal 4 and q equal 5. I chose a completely random alpha. I don't know which one. But in this case, the signature would be 6, because I have 6 red points, minus, well, whatever the other number of points are. They should be 14. So it should be 6 minus 14, which should be minus 8. Why? I guess that Livio will answer this question. And where does it come from? Well, this comes from algebraic geometry. It comes from computing equivariant signatures of Milnor fibers of hypersurface singularities, surface singularities in C3. And this is related to branched covers and a whole lot of different things that maybe Sashka will say something about.
Am I allowed to, I mean, is this true for every omega, or am I somehow implicitly assuming that there are no points on these lines?
You can make it work for when there are points on the boundary, since whatever we care about is for signatures almost everywhere. There are finitely many points at which, finitely many alphas for which you have 1 point on the line L alpha or on the line L alpha plus 1, and I'm happily ignoring those points. It so happens that for those values, for those exact values, the signature is the average between what happens before and what happens after.
So it's not 0, and at those points, it's not a 0 form, something like this.
So I think that you just ignore the point. If it's exactly on the line, it's neither blue nor red. Or half blue, half, it's a half blue, half red if you want. Yeah. Yes.
Marco?
Yes.
Signature function is locally constant in between the roots of the alternator formula, right?
Correct.
So if one of these lines does cross a dot that changes the number of reds and blues in an equal way, does that mean that that's what the root of the alternator formula?
Correct. So the alphas for which one of the integer points that I drew lies on the line are exactly the alphas that correspond to roots of the Alexander polynomial. And we'll, yeah.
All of them? All of them?
Yeah. And indeed you have p minus 1, q minus 1 points. So you have p minus 1, q minus 1 lines for which this happens. They're all distinct. No 2 points lie on the same line. Everything works. It's surprising, but everything works. So, what can we do with that? We can prove Litherland's theorem. So what do we want to prove? Let's recall that we want to prove that positive torus knots are linearly independent in the concordance group. So we want to prove that no linear combination of torus knots. So let me use the sum notation. I have sum of mi, ti, tpi, tqi, a linear combination of torus knots. The concordance group is abelian, so it's fine to use this notation. I'm taking mi, the connected sum of mi copies of ti, pi, and I'm taking the connected sum of all of these. And I want to prove that this is non-zero as an element of the concordance group. In other words, I need to show that this is not slice. Not being slice means that the slice genus is at least 1. So one way that I have to prove that something is not slice is to prove that the signature does not vanish. Because if the knot is sliced, then the signature vanishes almost everywhere. I want to show that the signature of that linear combination is not 0, almost everywhere. So this is implied by the signature of this big linear combination that I will call very dramatically K is not almost everywhere 0. Right? Is the goal clear? And now we have a way of computing the signatures for these knots, and we can try and play with some, well, not even linear algebra. At this point, it becomes really just combinatorics and a tiny bit of number theory to prove this. So I will make 2 claims. Claim A. So as Jeff was saying, I don't know if everybody heard this, but the signature can jump only at the zeros of the Alexander polynomial. This is a continuity of eigenvalues principle, or continuity of roots of polynomials. If you have roots that, if you have a family of polynomials that has real roots and never has the 0 root, then the number of positive eigenvalues and the number of negative eigenvalues stays constant along this family. And in particular, there's no change in the signature if you consider as a family the determinant of a family of matrices that are non-singular. So in between 2 roots of the Alexander polynomial along the unit circle where omega lives, the signature stays constant. So it's not locally constant, it's not piecewise constant, but it's something similar. It has stretches along which it is constant, and then it jumps. So somehow the interesting places are not where it's constant, but it's where it jumps. So the signature, the first jump of the signature of TPQ is at alpha equal 1 over PQ, and it's a negative jump. So you can actually see from that picture, if you take alpha equal to 0, you're splitting the rectangle exactly in half along the diagonal, and you have as many red points as you have blue points. And if you move a tiny bit, this stays, you're actually not meeting any point for a bit. So the signature near 0, near 1, so this is as 1, this is 1. I'm going in this direction, and for a tiny bit, the signature is 0 here. This is actually a slightly more general fact that maybe you will prove at some point, that the signature of a knot is always 0 near 1. But for torus knots, you can also see it from this theorem. Yes?
Does the Litherland
So if one of them is negative, you just change signs. Yeah. Yeah, no, this is for positive torus knots because this comes from algebraic geometry. But I'm supposing that P and Q are positive to draw that even. So there's a point here, which is when alpha is equal to 1 over PQ, where you jump. And you jump at this point, and you jump by -2. So the signature becomes -2 after this point. That's the first claim. And the second claim is that the first positive jump of the signature is at alpha equal to P plus Q over PQ. I'm not sure that I will prove these claims, but let me see how the two claims together combine to prove the theorem. So these are two easy remarks, two easy claims. And let's see how claim A plus claim B so let's pick this linear combination. And let's filter it out by looking at the products Pi, Qis. So let M be the max of the products Pi, Qi over all i's. So if that linear combination is slice, the signature is 0 almost everywhere. And in particular, it cannot jump at 1 over m. So let's look. So suppose, up to reordering, I can suppose that P1 Q1 is equal to P, I did not give it a name, that's good. PL QL is equal to M, and then PK QK is less than M for all k larger than L. So I'm taking the largest one first, and then I'm taking the rest. Then I need, so no jump at 1 over m, at alpha equal 1 over m, implies that somehow all the knots up to the first L's have to have signatures that cancel out. So this implies that the sum for I from 1 to L of mi is 0. Because the first jump is -2 times m1 for the first knot, -2 times s2, m2 for the second knot, and I need them to cancel out. So I'm arguing by contradiction. If that knot were slice, then the signature would be constant almost everywhere. Well, it would be 0 almost everywhere. And so there would have to be no jump. Yes, thank you. But now, let's look at what happens. Let's also suppose that P1 is less than P2 is less than PL. And let's see what happens. Now I need to think about it for a second, at PL plus QL over PL QL, which is the smallest among all PI's plus QI's between 1 and L. So this is less than PL minus 1 plus QL minus 1, PL QL, PL minus 1, QL minus 1, and so on. So this is the first point on the unit circle at which we see a positive jump in that family. So here we see a positive jump of the signature of T, PL, QL, but not of any other T among TP1, Q1, TPL minus 1, QL minus 1, because it's too early for them to have a positive jump. But no positive jump. So if they have a jump, it's a negative one. And actually, and no other TPIQI even have a jump there. Neither positive nor negative. This is why. Why is this? This is because the jumps, actually if you see it, if you look at that picture, if you squint at it a bit closer, the only jumps can appear of TPQ can appear when alpha is of the form K over PQ. So the numerator has to be divisible to be a divisor of PQ. And this fraction is already a minimal fraction. So the numerator of this fraction is actually PLQL. There's no simplification. So if PQ is less than M, there's no jump there for any of them. So what is happening is that the sum of the mi's has to be equal to 0. And there's a positive jump of the first one, but not of the other ones. And in my head, this implied that there's no further simplification here. So in particular, if L is non-zero, then there's a positive jump at this point that is not compensated by any other jump. You need to play a bit with what happens here, but in my head this worked out, and I think I wrote it down on paper, and right now I don't see it immediately. So maybe I'll come back to that if I'm too confused, or if I'm being too confusing. I just wanted to say briefly, very briefly, how you prove these two claims. So when do you get a positive jump? At the beginning, at alpha equals 0, you have all blue and all red. And the first time where you have a jump is when you have a point that switches from red to blue or from blue to red. The first point when you see a new red appearing is for this line here that I will draw in red. And this line here is the line that passes through the point 1, 1. And the line that passes through the point 1, 1 is the one that has alpha equal to 1 over p plus 1 over q, which is exactly p plus q over pq. The first time you have a negative jump, this is slightly more delicate, is the first time you encounter a point above the diagonal. And the first time you encounter a point over the diagonal is necessarily the point p q plus 1. My claim is that there is a point in here that lies on the line x over p plus y over q equal to 1. And this point is the point with coordinates q star, p star, where Q star is the inverse of Q mod P, and P star is the inverse of P mod Q. They exist because P and Q are coprime. Good, we're talking about torus knots. And it's easy to see that P star plus QQ star is equal to PQ plus 1. And that's the first point that you can have, because you cannot have anything that jumps at a point that is not of the form K over PQ, and this is the smallest of the numbers of the form K over PQ, so this corresponds to the smallest jump. Anyway, sorry, this was too quick to wrap up, but I think I'll stop here.